Welcome back. In this lecture, we will first compare the results of the simulation which I ran on the mesh that I used for Smagorinsky model with the layers, and I also ran the same mesh with the RANS model. I did this to make a fair comparison, because if the mesh are different, then the comparison is not that fair. I'll first show you the results of RANS. You can see here that the mesh that I have used is same mesh that I used for the simulation using the LES model with Smagorinsky turbulence modeling for subgrid scale. Here I'll first show you the velocities for 0.005. I'll turn on just the surface. Let me clip this along C, and I'll also open this LES simulation. I'll also clip this one along Z and invert this so that we have the other side. And here also see the decomposed cases. Let's look at velocity first. Let me also turn on the edges on both the meshes first to show you that the mesh is exactly the same. You can see the layers are also the same. Let me turn this off. And now let's compare. The bottom one is the simulation using the RANS model, k omega SST, and close to the wall you can see that the gradient of the velocity is same. Here also you can see this, but away from the wall the behavior is different. Here you can see there are two vertices. This vortex has moved a little bit more compared to this one, and this also have more advection compared to this one. The velocity of this vortex is higher. And if you look at the next step, so I have only two time solutions for the LES simulation. We'll look at only two results, and here also you can see it is much better resolved, but close to the wall the behavior is same. Clearly this Smagorinsky model does not resolve well close to the wall. Close to the wall the resolution and the subgrid scale that is required is modeled using Smagorinsky model, and compared to that the k omega SST model works much better close to the wall. Therefore there are some LES model which are a combination of this RANS model close to the wall and the LES model away from the wall. We'll look at them as well. We can see the results are decent, not that bad. We'll use this same mesh, and in this particular lecture we are going to go through the source code, and we are going to try one more LES model, and we'll see that what benefit we get when we use some other model compared to when Smagorinsky model is used. But clearly here you can see that compared to RANS, LES models works much better, but again these are computationally expensive. I'll close this and let's get started. Let's first look at the source code. Let me open the source code. Here if you go to the source directory in the source code and then go to the turbulence models, inside that you will find this turbulence model directly. Here you will find various other folders, and here you have this LES folder where you will find various LES models. We have already tried Smagorinsky, which is here. Now let's look at this Smagorinsky model, the header file for this. Here you can see it is defined that this Smagorinsky model from where it is taken, and what is this Smagorinsky model, which particular form is this. You can read here the form of the Smagorinsky model implement is obtained from the K equation model assuming local equilibrium, which provides estimates of both K and epsilon separate from the subgrid scale viscosity. Here this B is this, and then this D is this, the derivative part, and Then K is obtained from D like this, and then you have the SGS viscosity, which is derived from this. Here delta is used, where this delta is derived from the delta model that you use. For delta, you have these all functions. We have used cube root wall as well as this max delta xyz. You have other options here as well. This one also we tried. Simple cube root of cell volume delta using incompressible LES models. These are the coefficients. You have to use an underlying geometric delta and then use this particular method to modify that depending upon the incompressible LES model. So this one should be used for incompressible flow only. You can go through the details of this, or you can just go to the reference paper, which is not here. So you can just go to the code and see that what it is doing. We are not going to do that here, and we are going to stick to cube root wall or the one we have used after that. We are not going to play with this, but these are always helpful because sometimes this cube root wall is not an accurate measure of the delta at that cell level because of the high aspect ratio of the cells. In that case, you can use max delta xyz, but this also overestimates the delta, and in that case you have to use some other delta depending upon your requirement. Let's look at another LES model, which is this WALE. Here, wall adapting local eddy viscosity. This will have a better behavior close to the wall. This is how we can use it. So let's copy this and we'll go back to our folders. I'll copy this FPS LES layers to here. I'll just change the turbulence model. We'll go to the turbulence model in the constant folder. Here you can change to here. We can just say that this is WALE, and as soon as you switch to that one, it will use these coefficients, so you don't have to do anything else. You can see here, just running pimple foam, you'll see that it is using WALE coefficients, and the turbulence model it is using is WALE. Let's look at the source code a little bit more to understand what WALE is doing. It is wall adapting local eddy viscosity. That means it might use the wall distance. Let's see if it requires that or not. Let's run this and see if it runs one iteration. If it ran one iteration, that means it does not require wall distances. And let me also make sure that we have not accidentally passed the wall distances. Here we have not calculated the wall distances. Now let's look into the code. Here this derivative symmetric part of the stress tensor is passed here, and this is the calculation for the kinetic energy K, and this is the SGS viscosity. Now let's look at here that how it is calculated. This is how K is calculated. This is ST, which is just the usual derivative symmetric part of this, and not doing much. Here the K is calculated like this, which is taking the symmetric part of the grad U, and then the calculation of this newt is same as before. This is square root of K. This K is calculated from this. Actually it's not the same. It is taking this grad U, and then using that it is calculating this. Other coefficients are here. They have their default values as well. We'll just run this and see how this particular change, which is the calculation of K compared to Smagorinsky, which is here. We can see that it calculates K using this particular relation, which we can see here as well. K is calculated using this square root of this, which is coming from here, there is a k cube, therefore there is a square. Okay, I guess this should be inside the bracket, but anyway, whatever is the relation, you can use that relation to write this particular code where this k is the kinetic energy is estimated, and from this kinetic energy you can evaluate what is the SGS viscosity. Here that changes, and the change is motivated by the fact that it wants a wall adapting local eddy viscosity. Close to the wall, the viscosity should be higher. Let's see if close to the wall, clearly the stresses increases. Stress is highest at the wall, so that might be affecting the viscosity. Let's see how it affects the k value. Just 1 power change is there, except that there is not much change. Let's see the simulation. I'll run this simulation and show you. Let me run this. It has completed a few time steps. Let's visualize them. Let me switch on the surface with edges. That is not required. We can just look at the decomposed cases and then look at the velocity. So you can see here, in order to compare this with Smagorinsky simulation, I'll just clip this and open Smagorinsky side by side. Now let me open Smagorinsky, which was here, this one. I'll also clip this one along C and invert so that I have the other side. This one is the one which I wanted. Now let's look at velocity, both at 42 meter per second, and this one is Smagorinsky, and here we have WALE. Since, as the name suggested, you can see here in WALE, it says the wall adapting local eddy viscosity. We'll first try to look at what is Newt for both the cases. This one is wall adapting, so clearly there is some difference in terms of Newt can be observed, but close to the wall the behavior is same, and this one is just Smagorinsky. And let's look at the velocity profiles of both the simulations. Close to the wall it looks something like this, and here we have this. Not much difference is visible, but here you can see that this is more exposed to the downstream compared to this one, but it is hard to say that which one is better, because we have to have a actual experimental results in order to compare. But you can see that you have different results with two different turbulence model, and WALE is modified to have the eddy viscosity wall adapted. Therefore you should assume that this should be better, but again, without qualitative or quantitative results we cannot say for sure. Let's look at the next time step. Clearly this one is WALE, and this has completely different behavior compared to this one, and I think we have only two time results. Let me just confirm. We have three. Let me reload that, and let's look at the next one. Clearly the change starting from here keeps on increasing, and now we have completely different profile. And let's look at the entire flow, and this looks symmetric. Okay, this is not symmetric at all. Maybe it is not symmetric along this as well. Let's look at pressure, and you should not expect symmetry for LES method because the turbulence is anisotropic. We can see here also, we can see some variation along the y direction, which we assume that it is a 2D simulation, but it is not. Along this slice there is symmetry, you can clearly see, And now let's try some other turbulence models. I'll try this one. These all models are pure LES models, and then we'll also try delayed eddy simulations, which are here, and they are with a blending of RANS model with the LES model. First, we'll finish this in this lecture. Let's try this one. I'll copy. First, I'll kill the running simulation, and then go back and copy this. We can go to the simulation directory, which is this one, and just change the turbulence model. So I'll just write the coefficients of K equation and then write here KEQN. Now let's try whether this is running or not. So this is still using WALE. Okay, we changed in the wrong folder. Let me undo this and open the other folder, which is this one, and go to system. In the constant folder, turbulence properties, here change to K equation and add the coefficients. This should be small. Here, since it says a K equation, therefore you should have K here. Let me just activate this, and this seems to work now. It is using a K equation and same delta function with quantized flavor. And let me now clean everything from the previous runs and clean the post-processing folder as well and run this. We have not decomposed. Run this. So in the scheme we need to make some changes. We have to just activate this since we are solving for K as well. The exact equation that we are solving, you can just find that in the literature. So in the solver as well we have to activate. Let me write K here and K final here. So it is running fine. We can also tail the log file. All these models have their own pro and cons, and you should go through the pro and cons of each and every model in order to find a suitable model for your particular problem. So we have solutions for a few time steps. Let us visualize that. Let me also clip this, and I'll also open some old results. I'll open this simulation for WALE, and along with this I'll also open the old simulation using the Smagorinsky model. I'll just transform this along the z direction by 0.8 so that we'll know which one is which by turning them on and off. This one is K equation and the middle one is the WALE model, and this one is the Smagorinsky model. Now let's first visualize velocity. Here this bottom one is K equation and this one is WALE. These two looks very similar, except this is much sharper compared to what is going on here. And if we compare this to Smagorinsky, you can clearly see this is much more diffused, but still we cannot say much about which model is going to work better because we don't have any information about the actual results. But one thing to note here is that in the K equation we are solving an additional equation. That means this should be better. The K equation should be better. This one is the next time step. You can see this one is more diffused and the structure is not that clearly visible compared to what we see here. The structure is much clearer. And let's see the Smagorinsky. Here also the structure is clearer compared to the WALE model. Let's see the next time step. For this one, we can see what we have observed in the previous time step. For this, we are observing that here now, but the location of the vertices, which is in the wake region, which is creating this wake region, is very close. They are similar. Here also, the structure here as well as here, they are very much same. Close to the corner, we can see two vertices forming, whereas here we have only one and two smaller ones. Clearly, there are some differences, and to ensure that which one is better, we should do some qualitative and quantitative comparison with experiments or some other established results. We have seen these three models. Let's also look at one more model, which is this Deardorff DiffStress. Let's see how we can use this. In order to see that, so we do not have any examples which uses this particular model. We are just going to use this as is and see if it works for us or not. We'll again create one more folder. And I'll kill this previous simulation which is running. There is something else also running. Let me just check. There were two simulations which were running. Okay, so I killed both of them. Now let's edit this new one. First of all, just go to that new folder and let me close all these. This one is a new folder. In here we have to go to constant and then turbulent properties. Here we'll just write Deardorff DiffStress, and let's also check whether we need to have some coefficients or not. So these are the coefficients CK, CM, CE and CS, and here we can see whether there is any default values or not. There are already some default values. We are going to use the same values, so no need to write them. With this, we are going to go to FPS LES Deardorff and remove the old simulations, the post processing, and then the old simulation folders. Try just running this. We need R. Clearly, since we need R, that means this is going to use the Reynolds stress tensor, and for that we have to first solve a steady state and then use that to initialize this. Let's do that. In order to do so, we can just run a simulation here. In RANS, we can run one simulation. So in order to find the Reynolds stress at initial time, we can just run the RANS simulation and get the stresses at very small time step. So in order to do so, we'll first go to the RANS simulation. Here in the RANS simulation, in the control dict, we'll write the results for a very small time, and then we'll post process. We'll just write one time step. We can write the end time as that only. And now let's go to FPS RANS layers, and for this we can just simply run PimpleFoam. Okay, we did a mistake, so this should be same, then only we'll get the value at the same time. So now we can post process this particular result to output the Reynolds stress. Let's visualize this first. Here we have the velocity field, and for this we want to dump the Reynolds stress. For this we will just do So in order to post process, you can write ImpleFoam, then post process. You don't have to write a post process function explicitly. You can just write that function you want R, which is standard for Reynolds stress, and then you can write that you want it for the latest time, not for all the times, and then just press enter. The latest is invalid. Let's do this. Let's see. Now we have this. This we can directly use instead of that in the 0, because this is very small time. This is not going to matter much. And this we can use here in Deardorff 0. Just copy that here and rename this as R. And here also you can write R. Now let's go back to the original folder, Deardorff, and now again try ImpleFoam. It will ask for the solvers. Clearly this is what we have to use now, because when we are solving for Reynolds stress, we are solving for that stress directly and we are not taking as effective viscosity there. Therefore, we have to switch in the scheme. Let me close all this so that we are sure that we are editing the correct file. Here, go to scheme, and instead of this, we need to have this, and you can write Gauss linear here and switch this off. Let's see what else is required. We do not have anything for R, so dive R. For dive R as well, we can have Gauss linear, and then here also we can add the solver, or let's wait for the error to come up. This is still missing, and here also let me just add it, R and R final. You can see the initial residuals are high because we have used Reynolds stress, which is non-zero, but again this will stabilize after a few iterations. So it ran one iteration, one full time step. That means there is no problem. I'll stop this and then remove all the solutions that are there and the post processing as well, and then run using the parallel processor. First I have to decompose, then run ImpleFoam like this, and then we can also run the monitor to see whether it has started running or not. A file was created, but it has not completed the run. It has completed a run for few steps, so 1 2 3. So now we'll wait for this to complete and then we'll compare the results. So this particular simulation that we ran gave some error. Therefore, what we are going to do is we are going to copy everything from here, which is the RANS simulation, which is here. We are going to copy everything, not just R, so that these are compatible, and copy it here. Now I have to delete the old ones. Let me just delete everything from here and again do a copy. Yes, and rename this to R. And now we can try running it, just a single core run, and we'll see that whether this is working fine or not, and then I'll run the simulation in parallel after this. So you can see the errors are lower compared to what we have seen before. Now I'll run this in parallel. This particular simulation again gave an error. We'll just visualize what is going wrong by writing these solutions more frequently. Let me run this again. Let's first look at the log. It ran up to this. We can safely have this as our write interval, and I'll again run. We have at least one. Now let's visualize. So these R values These does not look fine because the stresses here are too high and the velocities are low. Let me do one more thing. Let's see whether we have any kind of boundary condition for R. There are no boundary condition at all. Do we have something for U? For U we have this has no slip and we still have these. So probably this is causing an issue that these sides should be empty. We try to put this in here and then try. For R this should be empty. And let's try now. Also, we do not have any boundary condition for R. We need that as well. Somehow the boundary conditions were not derived for this R, and the solver may not be able to find that what should be done at the boundaries. I think that might be causing some issues. Let me again open this and let's see how this R is behaving. We have this much results so far. This XY, there's some values here in YZ and XZ. Okay, now let's just look at the magnitude and with time how this is behaving. There is not much change. Let's look at velocity. Velocity has increased a lot somewhere. Let's find out that cell. We can do that by doing a threshold. So that because this is not a scalar, it won't do it for it. Without doing that, let's look at pressure. Pressure values are also very high. Let's do a threshold on pressure. Anything greater than 100 and negative 100. Let's do greater than 100 and this lower threshold, and the higher threshold is, so in this region we have a very high values. Very close to the inlet also there is some problems. So that could be an issue of how we are setting the inlet, and there is nothing that is set for the inlet, which is strange because in the lecture on LRR, on doing this post-processing, we are able to get the values for boundary condition for inlet, outlet and the boundaries as well. You can refer to that particular lecture, but for this particular lecture we are going to stop here, and in the next lecture we are going to talk about these models, which are a blend of RANS and LES models. Here we are going to talk about this delayed eddy simulations. We have the k omega SST DDES model, and then we have k omega SST IDDES model. You can see here it's this IDDES model, and then the simplest one of these is Spalater-Lemons DDES model. We'll try these three models and we'll talk about these three models in our next lecture.
Thanks for watching, and if you like the content of our channel, then please like, comment, share and subscribe.